In this video, I will demonstrate a process in which you can determine which type of statistical analysis you will choose based upon the data you have collected as well as the research design that you may be using for a research project. Now, typically one of the more difficult and maybe fear-inducing parts of research process, at least for students and people that I've worked with, is choosing the correct statistical technique to analyze your data. Now, in many courses you will learn how to do the actual analysis technique in SPSS or other statistical software, but we spend a lot less time kind of teaching people or teaching students how to choose which approach is most appropriate to address their particular research question or address their data. So in most research projects, it's highly likely that you're going to use a variety of different types of statistics, and it depends on the question you're addressing and the nature of the data that you have. And so it's important that you at least have a basic understanding of the different statistical tests, the type of questions we're going to address, and the underlying assumptions. So in choosing the right statistic, our goal is to really match the research design that we have to the appropriate analysis. And if we have multiple research questions or designs, we might have multiple analysis techniques we will have to choose. And so I find it to be really useful to follow a step-by-step process in which we have three basic questions that we need to address and answer. The first question we need to address is what type of research question are we asking? And then typically we put our research question into one of three types, which I'll cover in a short time. The next question is what type and number of variables do you want to or are you attempting to analyze? And then what type of data do you have as far as the scale of measurement? And then what characteristics does this data have? So the first step in this process is what question type do you want to answer? And so when we develop a research question, we can research questions, we can categorize it into one of three main types. And the first type and the simplest type is a descriptive research question. And so this is a situation in which you're just attempting to describe a group of subjects or a group of data, or you're trying to determine what the typical or what the normal characteristics might be in a group of individuals. And so we're not intervening in any way, we're not applying any kind of experimental treatment to a group of people, we're just studying them as they are, and we're just describing them in a relatively simple way. So an example question of this might be, what's the typical or average blood pressure for people in a given population? Survey research and observational research are very common designs that we see being used in descriptive research questions. Now the next question is referred to as correlational or predictive. And so in this situation we have groups of variables that we're trying to develop a relationship between, or we have a group of variables that we're trying to use to predict one another. So an example of this might be, is there a relationship between someone's blood pressure and their socioeconomic status? Another might be, can the neighborhood you live in predict your blood pressure? So what we're trying to do is establish some kind of a relationship among variables. And again, we're not intervening in any way, and we're typically doing observations, but we're trying to establish a little bit of a more complex type of research question here with correlations or predictions. And then the third and most complex type of question type we have is the cause and effect, or the group differences question, in which we're trying to compare groups to one another to see if there are statistically significant differences between them on one or more outcomes. And so an example of this might be, is the typical blood pressure higher in one residential area compared to the other? Do males have a greater incidence of depression versus females? And so in this case we're doing that group comparison. So what you have to establish in your situation is, what kind of question type am I trying to answer? Because there are going to be certain types of statistical analysis techniques we will use depending on the type of question we're trying to ask. So it's really important to be able to try and categorize your research question into one of these three types. Now, what I want to do next is kind of give an overview of some of the common statistical analyses techniques that are out there and the ones that I'll be giving examples for in this presentation, just so we're clear as to what these might be. So the first and most basic kind of analysis we can do in statistics is descriptive analysis. So this is where we're determining the frequency of something occurring, the percent of a group in which a certain outcome is occurring. So what percentage of people said yes, what percentage of people said no on a survey. We could develop percentile ranks. We could have measures of central tendency being mean, median, and mode. We could also be measuring the variance using standard deviation. And then we could also be developing standard scores like a z-score. Now the next level is correlational analysis, and two of the more common kinds of correlational analysis we can do is the Pearson correlation, which develops this relationship between two variables. So when we want to explore the strength of the relationship between two typically continuous or numeric variables, we can use this Pearson correlation. We can also use another technique called the Spearman correlation. So this gives us an indication of both the direction, either positive or negative, and the strength of the relationship. So a positive correlation means that as one variable increases, so does the other, and a negative correlation indicates that as one variable increases, the other decreases. Now regression is a technique that we use in which we're again using correlations. It's a little bit more sophisticated extension of correlations, and it's used when we want to explore the predictive ability of a single or a set of independent variables on one continuous or numeric dependent measure. So there are different types of multiple regression that allow us to compare the predictive ability of particular independent variables and to find the best set of variables to predict a certain outcome. Now the next set has to do with analyzing differences between groups. And the first and the simplest are the t-tests. So t-tests are used when we have two groups, for example males and females, or two sets of data, a pre-test and a post-test. And we want to compare the mean score on some continuous or numeric outcome variable. Now there are two main types of t-tests. There is a paired or dependent samples t-test, and we use those when we're interested in changes in scores for participants or subjects tested at one time and then again tested at a second time, perhaps after some intervention or some event. The samples are related because they are the same people being tested each time, or in this case being tested twice. An independent samples t-test is used when we have two different or independent groups of people, example males and females, and we're only interested in comparing their scores. So in this case we would collect information on one occasion but from two different sets of people. Now the next type is the one-way analysis of variance, or one-way ANOVA. So this is similar to a t-test, but it's used when we have more than two groups and we want to compare their mean scores on a continuous or numeric variable. It's called one-way because we're looking at the impact of only one independent variable on our outcome. And so a one-way analysis of variance will let us know whether our groups differ, but it won't tell you where the differences are between the groups. So if we have three groups we're comparing, a one-way ANOVA will tell us there's a difference somewhere, but it won't tell us if one is different than two, if two is different from three, or if one is different from three. And so in that case we conduct what are known as post hoc comparisons to find out which groups are different from each other. Now you could also choose to test differences between specific groups rather than comparing all the groups, and these are known as planned comparisons. So similar to t-tests, there are only two types of one-way ANOVAs: a repeated measures ANOVA, the same people on more than two occasions, and between groups or independent samples ANOVA, where we're comparing the mean scores of two or more different groups of people. Now the next is known as a factorial ANOVA, sometimes referred to as a two-way ANOVA or three-way or four-way ANOVA depending on your situation. And this allows us to test the impact of two or more independent variables on one numeric dependent variable. So the advantage of using the two-way ANOVA or the factorial ANOVA is that it allows you to test for an interaction effect. In other words, when the effect of one independent variable is influenced by another, So, for example, if you suspect that blood pressure is higher with age, but only for males compared to females. It also tests for what we know as, or what we call the main effects, and that's the overall effect of each independent variable by itself. And there are two different kinds of factorial ANOVAs. There's between groups ANOVAs, when the groups are different from one another. And then there's repeated measures ANOVA, when the same people are being tested on more than one occasion. Now, some research designs combine between groups and repeated measures in one study. And this is referred to as mixed between within designs, also known as split plot ANOVAs, or also known as factorial repeated measures ANOVA. Now, the last one we can talk about is the multivariate analysis of variance, also known as MANOVA. And that's used when we want to compare groups on a number of different but related outcome variables. So, for example, we might want to compare the effects of different treatments on a variety of outcome measures. For example, depression and anxiety and quality of life. So we can have a multivariate ANOVA that can be done in a one-way, a two-way, or other more complicated designs if we have one or more independent variables. So those are the kind of an overview of some of the more common statistical analyses that you will have to choose from as you're making your decision process. So once you've identified your question, and again, based upon this slide, if you have a descriptive research question, you're probably going to choose one of the techniques from descriptive analysis. If you've got a correlational research question, you're probably going to choose something from the correlational analysis. And then if you've got a cause and effect or group differences question, you're going to choose one of the analyzing differences between groups options. So that's our first step. Now the next step is to identify and define your variables. So in other words, what is it that you're going to be studying? And so you'll need to decide what your independent variables are going to be. Now in a descriptive research question, you probably aren't going to have an independent variable. And in a correlational research question, you may or may not have independent variables. But certainly in a cause and effect question, you will have to have an independent variable. So that's the thing that you as the researcher are defining or manipulating. You're going to decide to give one group a treatment, another group a placebo. You're going to decide to compare males to females. You're going to decide to compare football players to basketball players. And that's your independent variable. And then you also have to decide what your dependent variable is going to be. What's going to be your outcome? Is it going to be blood pressure? Is it going to be body composition? Is it going to be muscular strength? That's what you need to identify as far as what your variables are going to be, and then how many of those you want to or are going to have. Your next step then is to come up with an operational definition for each variable. So for example, if you're deciding that you're going to do some kind of a medication as your independent variable, and maybe you're going to have different dosages of those medications. Or maybe you're going to have different types of medication that you want to compare. So for example, you might have medication A and then a placebo and then medication B. So you'll need to operationally define what each of those variables are going to be, and in the case of a dependent variable, how you're going to measure that. So if you say that IQ is going to be your dependent variable, well, there are several different ways to measure IQ and actually several different ways to define intelligence. So you'll need to figure out what that's going to be. Now, there are different ways to very often measure the same outcome. So, for example, if you think about someone's health, you can classify someone as an outcome into a category, healthy versus not healthy. Or you could give them a specific kind of measurement. You might measure their blood pressure as your definition of being healthy or unhealthy. And so you'll need, as you think about your operational definition, you'll have to think about the different ways you can measure those as well as define those. Now, the next thing you need to figure out is what is a normal or expected range of scores and how many levels of each variable will you have. So in the case of an independent variable, for example, you have to decide, do I want to have 2 groups, 3 groups, 4 groups, and so on. Now, as far as the outcomes are concerned, you'll need to have an understanding of what a normal or what a kind of a typical or accepted range of scores might be for your dependent variables. So if you're measuring blood pressure and you decide, someone having a blood pressure lower than a certain number is not considered to be a valid measurement. So you'll have to make those kinds of determinations as well, and that goes into just deciding what your operational definition is going to be. Now the next step is to identify the nature of those variables. So we've kind of identified how many we're going to have, we've given them a definition, we have an understanding of what the typical or acceptable range would be for each of those variables. So we next need to determine the level of measurement for each variable. When we think of the level of measurement, we often refer to this as measurement scales. So we need to determine whether each of your variables, as we mentioned before, is an independent or dependent variable. And it's really essential that you're clear in your own mind and in your research questions concerning the relationship between your variables. Which ones are doing the influencing, that's your independent, and which ones are being affected, that's your dependent variable. So the scales of measurement we use, the first of all is what's known as the nominal or categorical scale. And this is categories, basically, male versus female, what state you live in. Do you have a disease or don't you have a disease? Are you getting a treatment or are you getting a placebo? So that's the first level of measurement. And again, you'll need to figure this out for each of your variables. The next is ordinal, and this is basically a ranking. Did you come in first? Did you come in second? Did you come in third in the race? You can also consider this to be level of agreement or level of satisfaction. Do you strongly agree? Do you agree or do you disagree? Are you very satisfied or unsatisfied? So those would be considered rankings or ordinal scale. And then lastly, we have our numeric or continuous scale, also referred to as interval and ratio scale. And an interval scale example would be temperature, body temperature or air temperature. There's no absence of value in interval, but there is a kind of a sliding scale that we use for that type of measurement. Now ratio data has a set 0 point, so there could be an absence of value. So an example of this could be the number of books that you checked out from the library or the number of servings of vegetables you ate today. That could be 0 or it could be 100. So that would be an example of ratio scale. So again, each scale of measurement, depending on your variable, will have a different way that it needs to be analyzed. So we have very specific techniques that help us analyze a categorical outcome versus a ratio scale outcome. Now there are some situations in which you might want to change the level of measurement for particular variables. So you can change, for example, a numeric outcome into a categorical outcome or an ordinal level outcome. And so this can be really useful as you start to think about the different kinds of analyses that you can do and also some of the later on criteria that we'll talk about. Now, some additional information you'll need to identify about the nature of your variables. Now, for numeric variables, one of the biggest additional pieces of information we need to develop is whether or not the scores in our groups are normally distributed. In other words, do they form a bell curve as far as the frequency of occurrence? And that is a hugely important criteria when we talk about some of the different kinds of techniques that we need to use. Also, does your data contain an appropriate range of scores? Are there scores that don't make any sense as far as what would be a typical measurement, or are there scores that are much, much different than the majority of the scores, which we refer to as outliers? We need to identify if we have those, and that could have an impact on which analysis technique you will choose. Now, if we have nominal or categorical outcomes or independent variables, are the groups equally balanced? Do we have maybe 50 people in group A getting treatment A and only 10 people getting treatment B? That could certainly have an effect on which analysis technique you would use. Are some of the categories empty? For example, if you have a categorical outcome, but you don't have anyone that fits into category C versus A and B, that could have an impact on how you're going to be able to analyze your data. So those are some additional things that you need to think about and keep track of as we begin to choose the analysis technique that we use. Now the next step, and I think one of the more helpful steps as people go through this process is to actually draw a diagram or draw a picture of what your analysis might look like or what you're trying to accomplish. So I often find that people are kind of at a loss for words when trying to explain what they want to research and what they're trying to accomplish. So a lot of times it's easier and much clearer to summarize the key points in a diagram. So the idea is to pull together some of the information you've collected in the first 3 steps and put it into kind of a simpler format that will help you choose the correct statistical technique. And we'll go through some examples later on. So one of the key issues you should be considering is what we talked about in step number 1, is determining what kind of question you're asking. Are you asking a descriptive, a relationship or correlational question, or are you making group comparisons? So we want to summarize the key points in a diagram. And so again, as I mentioned, we want to identify the type of question we have, identify the variables, especially the number and the type of variables as specifically as we can, because it'll make a difference if we have a categorical outcome versus a numeric outcome. And so an example here is we want to determine that if there's a relationship between blood pressure and body weight. And a giveaway here is the word relationship. When we say that we want to determine the relationship between 2 variables, we're talking inherently about a correlational research question or a prediction research question. And so in this case, we want to determine that relationship. So we have 2 variables that we're working with. We have body weight, which in this case is a continuous numeric variable, and we're measuring body mass in pounds between 100 and 250 pounds. And then our other variable is blood pressure, again a continuous value, with this being kind of our accepted normal range. So we have 2 variables that are numeric or continuous in some way, and we're trying to compare them as far as looking at their relationship. So we could graph that out by looking at a scatter plot or a scatter diagram, in which along the bottom axis, the x-axis, we have one of our variables. In this, this is mislabeled, but this could be body weight. And then in the other axis, we have blood pressure, for example. And so we can kind of graph out the picture we are trying to develop. And so in this case, this would point us in the direction meeting the criteria of asking a relational research question or a correlational research question. So we would probably use the Pearson correlation technique. Now, another example. Do people with BMI or body mass index values below 25 have lower blood pressure, systolic blood pressure, than people with BMIs above 25? So I want to do this comparison between people in one group and people in another group. So that sounds like a cause and effect or a group comparison question. So we look at our variables. We have BMI, or body mass index value, which is our independent value. This is what we're manipulating using to categorize people. So it's a categorical variable. It's our independent variable. And we have 2 groups or levels, people with BMI below 25 and people with BMI above 25. Our outcome variable is dependent. The dependent variable is continuous as well, blood pressure, which has a particular range that we are used to seeing or expect to see. So how to diagram this? Well, the best way to do this is using a table. And so what we put in our columns along the top of the table are the independent variables or independent variable. So we know we have 2 groups in our independent variable, so we have 2 columns. We then put our dependent variable or outcome variable in the row of the table. And we have one of those, so we have 1 row. Okay, and we label this as our mean systolic blood pressure, and we're comparing that mean systolic blood pressure for people with this level of BMI versus the people with this level of BMI. And so that's how we can fairly easily diagram out what we're trying to accomplish. And it's going to be very helpful to visualize what it is you're trying to do. And we'll go through some more examples later on in the presentation. Oh, here's one more example. So in this example, we want to look at the effect of sex or gender on systolic blood pressure. and to see if it's different for people with BMI values below 25 versus people with BMI values above 25. Okay, so you might recognize this from our previous example, is looking at blood pressure comparing people with two types of BMI, but now we want to throw in the effect of gender or sex into the equation. So now we have three variables we're dealing with. We've got gender or sex, which is again an independent categorical variable with two levels, male, female. We have BMI value, which again is our independent variable, and it's also categorical with two groups or two levels. And we still have our outcome variable, blood pressure, that's continuous. Now, just like we did before, we want to develop columns and rows that will represent the different measurements we're going to be taking, and also based upon the different independent variables that we have. So again, we can see here we can have one of our independent variables representing the columns, so BMI and its two levels. But now we have a second independent variable, so now we're going to have two rows representing the mean systolic blood pressure for males and then the mean blood pressure for females. So now I have two independent variables being used to differentiate people based upon this single outcome measure. And so now I can look at this and look at this graph and say, okay, I have one independent variable here, and then I have another independent variable here, males and females, and then I've got still my single outcome. Okay. So that's just another example of how we can graph that out. Now, the next step that we have, step number 5. This is actually a way that we're still trying to determine kind of the nature of our variables. And so we need to determine if we're going to do a parametric versus a non-parametric statistical analysis. Now, parametric statistics are more powerful, but they do have quite a few kind of conditions or assumptions that we have about the data that are a little bit more stringent in order to feel comfortable using that level of technique. And probably one of the biggest examples of one of these assumptions is that the scores that we've collected as our outcome need to be normally distributed. Now, each of the different parametric techniques, and examples of this are the t-tests and ANOVAs, have additional assumptions as well. So it's really important for us to check and be current on what those assumptions might be, because it's typically going to be more than just normality. There's normality plus another, plus another, and plus another. So it's really important that you research adequately or are comfortable adequately with what additional assumptions might be. And it's important to check these before you begin to conduct your analysis. Now, if we don't meet the assumptions for parametric statistics, we have an alternative for many of the techniques that we use known as non-parametric statistics. So many of the attributes we might be measuring in our outcomes may not be normally distributed. And as a matter of fact, some typically are very skewed. So if we don't meet the assumptions of parametric statistics, we can then explore the options of using non-parametric statistics. So if it doesn't meet the assumptions of parametric statistics, what do? We actually have a few options. The first is to use parametric testing anyway, even if we violated some of the assumptions of parametric statistics. Now, and when we do that, we hope that it doesn't seriously invalidate or contaminate your results. Some authors will argue that many of the approaches, especially the more advanced types of ANOVAs, are robust enough that they can overcome minor violations of the assumptions, particularly if we have a large sample size. But if you decide to go ahead with the analysis of parametric statistics, even though you have violated some of the assumptions, you need to justify that. So if you're writing up your research, you need to justify the fact that you've done that. Now, your next option is to do something called data transformation. And this is where we can manipulate our data, but not in an unethical way. It's an ethical approach to manipulate the data so that we can transform the data so we can meet the assumptions, specifically normal distribution, for parametric testing. There's some controversy with the approach, but it is fairly well accepted. And I have some other videos that talk about how to transform data using log transformation. And so if you'd like to learn a bit more about that, you can. Your third option is to use what's known as a non-parametric technique. Now, for many of the commonly used parametric techniques that we have, like t-testing and ANOVA, there is a corresponding non-parametric alternative. So there are still some assumptions that come with non-parametric testing, but they tend to be a lot less stringent. And these non-parametric alternatives tend to be not quite as powerful, and so they're not as sensitive in detecting a relationship or a difference among groups. But it is an alternative. If transformation of data doesn't work, which sometimes happens, to transform your data to normally distributed, you might not have any option but to use non-parametric techniques. So to give you some examples, if you're assuming you're going to do a Pearson correlation on your data, for example, but your data is not normally distributed or violates some of the other assumptions of the Pearson correlation, you can use something known as the Spearman correlation for numeric data that's not normally distributed. Or if you have a categorical outcome, you could use the chi-square test for independence. So there is an alternative there. For the independent t-test, the alternative would be the Mann-Whitney U-test. For dependent or paired samples t-test, the non-parametric alternative is the Wilcoxon signed rank test. For the one-way ANOVA, the non-parametric alternative is the Kruskal-Wallis test, is some examples. Okay, your sixth and final step is to go ahead and make that final decision as far as what your analysis technique is going to be. And so again, to summarize, we're making determinations about the variables. You've identified what type of research question you have. We make sure we meet all the assumptions that are present for each of the different techniques that we might be considering. And we also think about, are there other approaches that could be taken? Maybe we can change our outcome in a way that we could use a technique that we're more comfortable with or that we think might be more appropriate to what we're doing. So it's always a good idea to think about what some of our alternatives might be and kind of have a list of possibilities, and then we can make a decision based upon that list, kind of doing a pros and cons approach. One thing that can be useful is to look at other published studies that have used similar designs and then look at what analysis technique they used, especially if you've got the same kinds and the same number of variables and the same operational definitions for those variables. That could be a really easy way to kind of help make a decision. And that gives you then some justification too. So if you're saying, well, I want to use this particular technique, and you can say this was done in studies by Smith and Jones and Carpenter that had the same variables, the same design, etc. And that lends some credibility to your decision. Now let's go through some examples of this process so you can see how this works, incorporating our different steps. So our first example, our research question is, what is the relationship between gender and having a diagnosis of clinical depression? So we see the word relationship there. So that should be a rather easy clue for you. This is probably a correlational research question. Okay, so that's one of the first criteria that we have. The next thing we can think about is what we have as far as variables. Well, in this case, we have one categorical independent variable, gender. In other words, we're assuming gender is going to have an impact on clinical depression or diagnosis of clinical depression. So it's a categorical independent variable with two levels, male and female. We have a categorical dependent variable or outcome, in this case a diagnosis of depression. Either they do or don't have clinical depression. And so one thing to note is we're not really measuring a score here, but we're measuring the number of people that fall into each category. Okay, so we have a categorical outcome. And so to graph this out, we could draw this table. So again, here in the columns are our independent variable, gender, male versus female, and in our rows we have our two potential outcomes, the two levels of our outcome, either has depression or does not have depression. Okay, once we've graphed that out, we start to look at some of the criteria. So when we talk about making group comparisons, you might say to yourself, well, I can do a t-test on this. Well, this is a non-numeric outcome, So we can't use a t-test. That's one of the assumptions of t-testing, is it has to be a numeric outcome. So because we have a categorical outcome, we can choose a technique known as the chi-square test of independence. Okay, so that will be the process of going through and deciding what technique would be used for that example. Now let's go through another example. Is there a relationship between age and depression index? Or in other words, does depression increase with age? Now again, relationship is the term here. So again, we're thinking correlational. But compared to the previous example, example 1, we had a categorical outcome, so we can't use the Pearson correlation in that situation because the assumption is that we have a numeric outcome. But we're still asking a correlational research question. So now what we have are two continuous or numeric variables, in this case age, and then score on a depression index, in this case the Beck's Depression Inventory, let's say BDI. So now we have two continuous variables that we want to try and relate. So we wouldn't use the chi-square test for independence because the outcome in that case is typically a category. Our outcome now is not a category. So we could graph that out similarly to an example I talked about early on. We've got age as being one of our variables, in this case what we would consider to kind of be our predictor variable, and then we've got Beck's Depression Inventory score as being our outcome. And so what we're trying to do is find the relationship between those two sets of scores. And so in this case we would use the Pearson correlation. We have a numeric outcome that we're assuming is normally distributed. If we had non-normally distributed data, our non-parametric alternative would be, or could be, the Spearman correlation. Okay, another example. Research question is, are males more depressed than females? In other words, is there higher levels of depression in one gender versus another? So what we have is one continuous outcome or dependent variable. In this case, we're still sticking with our depression index score. That's numeric outcome. We have one categorical independent variable with two levels. So our independent variable is gender, in this case with two levels, male and female. Again, graphing that out, we've got our columns with our independent variable, male, female, and we have our row being our outcome variable, mean BDI score. Okay, so two independent groups that we want to compare on one numeric outcome. The option here would be the independent t-test. Now, if we didn't meet all the assumptions of the independent t-test, a non-parametric alternative could be the Mann-Whitney U-test. Okay, example 4. Will 10 weeks of exercise training or performing exercise on a regular basis reduce someone's depression score? Will it reduce the BDI score? So in this case, we have one categorical independent variable, this being time, the passage of time. So we'll give them a pre-test of BDI, expose them to the training, give them a post-test, and then remeasure the BDI score. So this would be an example of a repeated measures type of a situation. The same group of people being measured twice, in this case before and after an intervention. Our outcome is still one continuous dependent variable, BDI score. So now we'd set that up pretty much the same way we did the previous example, with our independent variable going in the columns, pre-test and post-test, or measurement point number 1 and measurement point number 2, and then our outcome goes in the BDI score, goes in the row, the BDI score. Now in this case we have two groups or two sets of scores, pre-test and post-test, being measured for one numeric outcome, and this is a dependent group. In other words, it's the same people being measured twice. So using that criteria, we would choose the dependent or paired sample t-test to compare these two groups of scores. If we didn't meet the assumption of this test, the non-parametric alternative is the Wilcoxon signed rank test, or could be the Wilcoxon signed rank test. Now, a little more complex example. Are there differences in depression score for people under the age of 30, between the ages of 31 to 49, or older than 50 years? So what we have is one categorical independent variable, in this case age, with more than two groups. In this case we have three groups. We could make this 4, 5, or 6 groups. We have one continuous outcome, in this case the BDI score. So now to graph this would look very similar to what the independent t-test graph looked like, except now we have an additional column for our third group. So our three levels of independent variable, 30, 31 to 49, and then 50 years of age, and then one numeric outcome, mean BDI score. So in this case, our option would be the one-way ANOVA. Now, if our data was not normally distributed, or we violated one of the other assumptions of the one-way ANOVA, our non-parametric alternative is the Kruskal-Wallis test. Our next example, what is the effect of age on BDI scores for males and females? So what effect does age have on depression? What effect does gender have on depression? So as you hopefully were able to pick up, we have two independent variables, two categorical independent variables. Sex, male versus female, and then age group, under 30, 31 to 49, and greater than 50. We still have one continuous dependent variable or outcome, in this case our BDI score. Now to graph this out, we're going to have one independent variable being our columns, in this case age. We've got our other independent variable denoting two of the rows. So we see a male row and a female row. And here's our independent, or excuse me, our dependent variable, BDI score. So we can study the effect of age by itself, we can study the effect of gender by itself, and we can also study that interaction, that unique interaction between the two independent variables. Okay, so in this case, we would choose the factorial, in this case, because we have two independent variables, a two-way ANOVA would be another way to characterize it. Now, if we don't meet the assumptions of the two-way ANOVA, unfortunately, we do not have a non-parametric alternative. So in this case, you may need to reconsider how you are going to classify your outcome. You may want to change it into a categorical outcome. Maybe decide what BDI score would be a cutoff. You either have a high level of depression or a low level of depression. Maybe you change it into a rank. So those are situations where we may need to rethink our design. Now our next example, which of two therapy interventions is more effective in reducing BDI score across 3 time periods? A pre-treatment, a post-treatment, and then 3 months post-treatment. So let's look at what we have here as far as variables. We have what we call one between groups independent variable. So this is the type of intervention. So we have one group of people receiving exercise, another group of people receiving meditation. So that would be two groups between compared to each other. And then we have one within groups independent variable. In this case, our 3 measurement points, pre, post, and 3 months post-treatment. And we still have one continuous dependent variable, our BDI score. Now to graph this, again, we have columns representing one of our independent variables, in this case the time, passage of time. This is our within groups independent variable, time 1, time 2, and time 3. And then we have 2 rows representing the between groups independent variable, exercise or meditation, again measuring the same numeric outcome, mean BDI score. Now again, we can study the effect of time by itself, we can study the effect of the treatment by itself, or we can study a unique interaction between those 2 independent variables. But now there's a repeated measures component. The people that are in the exercise group are being measured 3 times. The people in the meditation group are being measured 3 times. So in this case, our technique would be that factorial repeated measures ANOVA, again sometimes called the mixed between within design or the split plot ANOVA design. Unfortunately, again, we do not have a non-parametric alternative here. So again, we might need to rethink what our outcome is going to be. Now our last example, might be, do males have better overall ratings of psychological health, such as levels of depression, anxiety, and perceived stress, than females? So what do we have here as far as variables? We have one categorical independent variable, in this case gender or sex, male versus female. But now we have two or more continuous outcome variables. So we're going to measure depression and anxiety and stress levels. So to graph this out, our columns again would be our independent variable, males versus females, and now our rows represent three different outcome variables. So each male will be measured on three different outcomes, and each female will be measured on three different outcomes. So we can compare the two groups to each other on three different outcomes. And again, the assumption here is that these three outcomes are related to one another. So our option here would be that multivariate analysis of variance, or MANOVA, because we have multiple outcome variables now. If we contrast this with the one-way ANOVA, where we just had one outcome but three groups, in this case we have two groups, but now we have three outcomes. And so we have a different analysis technique we would use, in this case the MANOVA. And again, unfortunately, we do not have a non-parametric alternative for this. So again, we might have to rethink this. So in summary, I've gone through kind of a simplified six-step approach to help you decide what type of statistical analysis technique you would use depending on your research design as well as the data you've collected. And to summarize, what we basically are going to do is we want to determine what kind of question we're asking, or questions we're asking, what the characteristics of our variables are, and then do we meet certain assumptions or certain characteristics for some of these different types of research or some of these different statistical analysis techniques. So hopefully this will help you in your research, and hopefully you've learned a little something about the process. So good luck using this in your own research.